All right, so I got a great question about this problem of instantaneous reaction rate, and I think in terms of rate in general, it's a great question. Um, so what happened was we went through and we calculated the reaction rate based on the disappearance of oxygen over time. All right, we went through and we wrote the expression for the reaction rate based on oxygen. And remember, we put this negative sign out in front. So when we get done, the reaction rate is equal to this positive number, 6 times 10 to the minus 7th molar per second. And the question was, well, yeah, so the reaction rate comes out to this positive number, so you would expect that the amount of oxygen would then be increasing, right? And the answer is no, not necessarily. When we calculate reaction rate is defined as a positive number. When we go through and write those expressions for reaction rate, if something's disappearing, we put a negative in front of it to make it positive. So when we write these expressions for reaction rate based on each of the individual species, and we're going to go through and do that in a second, we're defining them all to have a positive sign in front of them. Now, the thing that's confusing here is that, actually the question that I answered is different from what was asked. And it was asked to calculate the instantaneous rate of change for oxygen at t equals 2,000 seconds. So, first what I want to do is I want to write out the rate expression for each of the different components in the reaction. So remember, we would say that NO, it would be the change in the concentration of nitrogen monoxide over the change in time. And because it's a reactant, it would be negative. And it's got that 2 in front of it, so we would put the factor of 1/2 in front of it. And that rate is going to be equal to the rate based on the oxygen, the disappearance of oxygen. So the change in the concentration of O2 over the concentration of time. We'd put a minus in front of it because it's a reactant, and a reactant's going away, and the factor would be 1 over 1, or 1. And then we could write it based on the product. And the product is nitrogen dioxide. So change in concentration of nitrogen dioxide over change in time. Because it's a product, it's appearing, so it's going to have a plus sign to the rate, and it's going to have a factor of 1/2. And all those things would be equal. All right, that rate as calculated based on the nitrogen monoxide, and that rate based on the oxygen, and that rate based on the nitrogen dioxide would all end up giving us an equal number, and all of them are going to be positive. Now, when we talk about instantaneous rate of change, we're talking about that part right there, only the change in oxygen over the change in time. So if we go back and we look at the problem that we did, and I'm going to move this up just a little bit so that we can see. Sorry. All right, so we know that the rate is equal to 6.0 times 10 to the minus 7th molar per second. And we know that's equal to minus change in the concentration of oxygen over change in time, with this being our instantaneous rate of change. So if we wanted to calculate that instantaneous rate of change, all we would do is we would just divide both sides or multiply both sides by a negative. And so the change in the concentration of oxygen over the change in time is going to be negative 6.0 times 10 to the minus 7th molar per second. which is indeed negative because the oxygen is decreasing. All right. The concentration of oxygen is getting smaller. And so this is technically, and this is where I kind of spoke a little loosely and not properly, is that this is the slope part. This is not necessarily, okay? Because we're changing negative slopes to positive slopes because we report rates as always being positive. So I just wanted to make sure that I got that cleared up. I thought it was a great question and I wanted to share that with you. So hope that you all have a great day.